Hi, let's create a spreadsheet simulation to help us answer the TED-Ed frog riddle. I presume you've seen the video already. I'll link to it in the description. There's some question as to whether the math as it was presented in the video is correct. So let's create this animation with the facts that we know from the riddle. So the riddle states that we have two groups of frogs. You may lick one group. You have your choice. And you only live if there's a female frog in that group for you to lick. You lick all the frogs within a single group, and you only live if there's a female in there, because the females have the antidote. So it states that the two groups are called the clearing group, and there's two frogs in that group. I'll call them left and right. And there's a tree stand group, and there's just a single frog there. So it's a small group. It states that any frog is equally likely to be male or female. And we can simulate that in the spreadsheet using the ranBetween function. RanBetween 0 and 1 is going to return to us a 0 or a 1. And we'll have the zeros represent males and ones represent females. And we'll do 100,000 trials. Paste that. Copy. I'm going to paste over it with itself, but just in value form. So there's no more formulas here anymore. But we now have 100,000 trials of the scenario that you have three frogs, and they can be male or female, equally likely for any individual frog to be male or female. We can demonstrate that by calculating the average for each frog. So it's about 50% probability. Let's get rid of both decimal places. Okay, so it rounds to 50% probability. If we were to do the actual math, you would, and the probability would come out to be 50% for any individual frog, and our trials show that they round to 50%. So trials look good so far. But remember that when you lick a group, you lick all the frogs in the group, and the males don't hurt you. It's that the females are the ones that give you the antidote. So it doesn't matter if there's a male in there or not, but you definitely want at least one female to be there. So we want to calculate the femaleness of this group, which is really just, is there a female? So easiest way to do that is just use the max function, and it returns a 1 if there's any female present. Doesn't matter which frog, right? Because you're looking both of them anyway. So any female results in a 1, and two females also result in a 1, but two males results in a 0. Okay, so that's working as we'd expect, and sure enough, if we paste the average formula onto this column, we see that the probabilities are significantly higher finding a female if you lick the group of two in the clearing, and that's because you're effectively flipping a coin twice and hoping that at least one of them is going to be tails or heads, and the odds of having any one of those results go up with the more coin flips you do. And we've just shown that with the simulation. So it's very obvious that if you're presented with this situation, you should walk over to the clearing and lick that group of frogs instead of walking over to the tree and lick that single frog. But that's not where the riddle ended. The riddle goes on to give you a bit more information. So I'm going to copy that sheet. I'll make a duplicate here. So the riddle says that before you make your decision, you hear one of the frogs in the clearing croak. And even though you can't visually distinguish between the sexes of frogs, you can definitely hear the difference between a male croak and a female croak. So we're now told that without any doubt, without any ambiguity, one of the frogs in the clearing is male. Okay? And you saw, and this is not in the riddle. The riddle doesn't say you see it. I think it says you don't see it. But let's say for this next step that you saw which of the two frogs it was. You saw it was the left frog, let's just say. If you know that the left frog is male, then there is no possibility that that frog is female. because you just heard it. And you saw it croak and you heard it and it was a male. So it doesn't make sense to have any femaleness in the clearing L column anymore. It's now purely male. And what you've noticed is now the probability of finding a female in this group has dropped from 75% to 50%. So this shows you just how devastating that information is. That information that one of the frogs is for sure male is quite devastating. Now you might say, okay, well maybe that works with the left frog, but what if you actually heard the right frog instead? So I'm copying the original sheet, so back to the 75% probability for the entire group, and I'm going to make the right frog the male frog that we heard, and leave the left frog alone. We didn't see in this example we didn't see the left frog. We only heard that the right frog was male, and you get the same result. You get the same result. Doesn't matter which of the two frogs you heard. Your news is just as bad, and the numbers and the math shown in the TED original TED Ed video do not come to this conclusion. So unfortunately, the original video is wrong. It's definitely wrong. Okay, hold your horses. Maybe you didn't see either frog. You merely just heard that one of the frogs behind you is the male frog that's singing, and you can't tell which one. So you might say, okay, it's not fair for me to say that one frog is male and the that the right frog is male and the left frog we don't know, because I don't know if it was the right or the left frog. So let's do a completely different let's take a completely different approach by stating the problem a little differently. So let's say that, let's ignore the tree. We don't care about this tree frog. That's going to be 50% no matter what. But just looking at the clearing frogs, we know that there's a group of two, and we know we heard one, and we know that one is unheard. So the heard frog is definitely male because you heard it. The unheard frog has equal probability of being a male or female. That's stated as part of the riddle. So we can do our RAND between function for the unheard frog and get a 50% likelihood of finding a female there. And again, the entire group now has a 50% likelihood that you'll find a female in this group. That's the correct way to, well, I would say this is the simplest way to think about the problem, is that you have a set of two frogs, one you heard, one you haven't heard. They have each has equal likelihood of being male or female. Now, what the problem with the TED Ed video is they actually alter the results effectively. What they're doing is they're altering the results of the unheard frog based on what you know about the heard frog, which is invalid. It's just completely invalid. You have equal probability of being a male or female frog for the unheard frog, no matter what you know about the heard frog. So that's just a completely invalid way to look at this problem, and gives you the wrong answer. In the conclusion of the TED Ed video is that there is a higher probability of going towards the clearing, and that would have been true had you not known that extra information. But that extra information is quite devastating and yields a 50% likelihood in all these scenarios. You either hear the left frog, you either hear the right frog, or you hear one of the two frogs, you don't know which. All of them yield the same result, which is 50%. Go ahead, average all the 50%, you get 50%. There's no other result that you can get, unfortunately, for the clearing group, so it's pretty bad news. So the correct answer is you can go to the clearing, you can go to the tree frog. Either will give you the same likelihood of survival. All right, so like some of the comments pointed out, this seems to have been an attempt to recreate the Monty Hall problem. So the Monty Hall problem is a specific riddle, and it's got different rules than the tree frog problem, than the frog problem that we just went over. So let me copy this sheet again. We'll recycle the sheet, but we have to change a few things because the rules are different. All right, so in this example, we have no trials yet except for the bottom one, which we'll keep there so it's easier for me to fill out the spreadsheet. All right, the Monty Hall problem states that one of the frogs is the correct answer, and only one. So no more than one and no less than one is the correct answer. And that's different than our frog riddle, or than our original TED-Ed frog riddle, because you can see that you can have one and only one be the correct answer, or you can have two be the correct answer, or you can have, as in this case here, you can have all three frogs be the correct answer. So it's a completely different situation than the TED riddle as it was presented, because the TED riddle, each frog has an independent probability. If this one's a female, then this one still is 50% chance of being a female. The Monty Hall problem is not that way. The Monty Hall problem does not have independent probabilities. So we can simulate the Monty Hall problem this way. We could say rand between, and we want to select a number between 1 and 3 inclusive, and this function will just generate a random, pseudo-random distribution of 1s, 2s, and 3s. I'll copy that onto itself, copy, paste numbers just as we did before, so those numbers don't change up on us, and we'll test this probability distribution here. 1, 2, 3. Actually, I want these to be numbers, no decimals. Oh my gosh. 1. Spreadsheet's not being that cooperative. There we go. 1, 2, 3. So count if count in this range whether you find the 1. And again, I don't want percentages. And I want to lock this range. And you see that they're pretty evenly distributed. So we have about 33,000 of each frog, 33,000 examples for each frog, which is a third of 100,000 approximately. All right, so let's say if the pseudo-random integer generator between 1 and 3, if that equals 1, then return 1, otherwise 0. Okay. And we're going to copy that here into the second frog, but we want we're changing the index to number 2, and here we're changing it to number 3. So in the way I just constructed this, there must be one correct answer, and there can only be one correct answer. So I'll do this now for 100,000 simulations. Looks like I did something wrong. I did. I shouldn't have locked the row there, so let me fix that. Okay, I only want to lock the column. Look, you're getting a spreadsheet lesson too. Okay, so we've run the simulation. I'm going to copy it on top of itself. Copy, paste, number, and you can see here that one and only one answer is correct in every one of these scenarios. Of course, this is the probability of licking the group is this column C. Oh, actually, we have to fix that. It's still the same concept, though. We still use the max function here. Just copy it all the way down. Copy it, and then paste it onto itself. There we go. All right. If you haven't been looking up here, you might have missed it, but we've now successfully replicated the Monty Hall problem odds just that easily. So basically what this is telling you in the Monty Hall problem is that you have an equal chance of any of the three choices being the correct answer. And Monty Hall problem says that well, the conclusion is that you always go to the larger group because there's a concentrated probability. So that there's a concentrated probability that one of those two is going to have the correct answer. So let's state this one another way. We can say that we have a single choice over here on the right side, and we know that that's a 1 in 3 chance that the single choice yields the correct answer. Well, then obviously the larger group that has 2 out of the 3 frogs has a 2 in 3 chance of finding. And I just had a system malfunction there. I've recreated the Monty Hall version of this frog problem. The numbers are going to be a little different if you look at it by row, but I did 100,000 trials again. So overall, numbers are about where we were looking at them before. So yeah, you would always want to go to the larger group because you have 2 in 3 probability of finding the female frog there, the one and only female, whereas you have a 1 in 3 probability of finding the one and only female on the tree stump. So why is this interesting? Well, the Monty Hall problem is interesting because of the way it was presented to the participant in the game show, where it came from. So what Monty Hall would do when you got to this point in the game is before you made the final decision of which group to go to, he would walk over to the clearing where you had 2 frogs, and he would look at them, and he can tell by looking at them whether each frog is male or female, and he would pick one of the males if there were 2, or the male if there was just 1, and he would squeeze it. And you would hear it croak, and then you knew unequivocally that that is a male frog, and of no help to you as a person who needs the female frog's antivenom. So the participant is kind of teased into looking at this as a different problem. The participant is teased into looking at this as saying, well, there's only 2 choices left, and since there are 2 choices, and I know that it's not in the wrong choice, and so it has to be in one of these 2, so therefore there's a 50% chance of it being in one of these 2. And that's actually incorrect, even though that might feel viscerally the right and only way to look at this, that there are 2 choices, and therefore there are equal probabilities that the female frog will appear in either of these choices. That's just not true. This is different than the original tree frog problem that the TED-Ed video presented. In this version, you don't have independent frogs. In this version, if one frog is female, then the other 2 cannot be female, and that changes the whole game. You don't have scenarios where you have 3 females. You don't have scenarios where you have 2 females, and you don't have scenarios where you have 0 females, because you need to have 1 and exactly 1 female frog in your population. So it's not the same as before, where we can just touch 1. We can just write zeros to 1 and not affect the probabilities of the other choice. So the correct way to look at this, in my opinion, just the way I look at this, is that all Monty Hall did is he just showed you that one of the 2 is male. But you always knew that, because you can know that if you have a set of 2 frogs, and you know that only 1, the maximum number of females in that set is 1, then you know that at least one of the 2 has to be male. Maybe both are male, but you know at least one of the two is male. So for him to go over and squeeze a frog and reveal that it's a male frog is of very, very little relevance to you in your decision making as to which group you're going to go over and lick. I mean, it does help if you walk over to the clearing because, and which you should, by the way, because it's still a 67%. It's still twice as likely to find the female frog in the clearing as it was before. Just because he squeezed one of the frogs doesn't really change any of that. But it does help because once you go over there, you don't have to lick both frogs anymore. You just have to lick the one he didn't squeeze. Because you know that one's male, so there's no point in licking that one at all. So he did do a nice thing for us. So it's a little, we do have some relevant information when it comes to which individual frog to lick, but that's not what the TED Ed is asking. They're asking us to choose a group, and this is the right group every single time. Not every single time, but it's the right choice every time. Could be the wrong group sometimes, but it's the right choice to make every single time. All right, so very similar to the way TED Ed presented it, but not quite the same, is it?